All right, how's everything going?
Good.
So how many people succeeded in logging into the CTech server? Cool. If you have not succeeded, come and talk to me at the first break and let's try it together and figure out what's going on. It's possible if you added the course, no, if you add the course, you should automatically get an account. How many people here have finished P1? Okay, so if you finished P1 and you tried to submit it and were not able to submit it, and that was the only part that was missing, it's possible that you don't have a submission area set up. Okay, if you registered pretty late for the course, like in the past few days or the past week, you may not have an upload area. In which case, just hold on to your program, and once Scott gets back, tell him that you weren't able to upload. Okay, but talk to me again at the break if you're having an issue with submitting program 1. So questions up to this point on CTech P1, anything we've been doing so far. We're going to dig into program 1 a little bit more. We're going to dig into this question of variables and data types, and then we're going to start talking more about programming itself. So any questions before we start down that path? All right, cool. And I think I already said this, but if questions come up along the way, please, please, please just ask them as they come up, right? Don't save them for the end of class or for the next break. You get a question, ask it right away, because if you don't know the answer to a question, sometimes that stops you from making sense out of whatever else we talk about. And it's potentially unnerving to, look around and everybody else seems to know what they're doing and you don't understand something. It's not always comfortable to say, I don't understand this, right? It took me years of schooling to figure out that a lot of people who look like they know what they're doing really don't, but they're really good at faking it, and their plan is that I'll figure this out later, right? But they're actually hoping somebody's going to ask the question, right? So if you've got a question, if something's not clear, there's a really good chance that a lot of other people in the class have the same question. So don't ever hesitate. I've never had a situation where a student was asking too many questions, right? Or questions that weren't appropriate or something. It's always the opposite. People should be asking questions and they don't. So the more interactive the class is, the more interesting it's going to be too, because 3 hours is a long time.
How touchy is PuTTY for network connection? Like if we get a small glitch and network connections would shut down, because I kept getting sessions that would close.
At Clark or somewhere else?
At my house.
At your house.
Pretty reliable internet.
Yeah, I mean, if the internet glitches, but usually wireless internets don't glitch anymore, right? Phone line was a different story, but it should be pretty reliable. Now, it may time out after a while if you don't do anything.
Okay. No,
But if you're
network closing, it would say network connection loss.
Yeah, it should be pretty reliable, but who knows? Plus, with operating systems, sometimes they do things, the program starts running and it's like, oh, I should save power, I'll shut down the network interface for a little while or stuff like that. So there could be things going on, but usually it should be pretty solid. How many people here have Linux installed on their own system? So that's a really, really good way to go. And if you're CS, you're going to want to go that route eventually anyway. And Linux is pretty straightforward to put on a machine these days. It's kind of like download and boot from the flash drive and follow the instructions and then just wait a long while. And if you have an old machine that doesn't run Windows very well anymore, it'll run Linux great usually. You can run with just a little bit of memory, a slow CPU, and it's perfectly fine for an installation of Linux. So it's something to think about.
What would be the advantage of running that for this class?
Advantage would be you don't have to always connect to CTech when you want to do something, right? Work on your code or try some commands. You could do it just straight on your laptop. If you're somewhere where you don't have a network connection, right, you're kind of out of luck if you have to get to CTech. And if CTEC's being kind of temperamental and is dropping people or not accepting connections, that's kind of a drag. The other advantage is if it's your own Unix system, you have full access to everything on that system, including all the privileged administrative stuff. And if you really want to sort of dig into what's going on in your computer or potentially break it, right, you can do that if it's your own Linux system. It's very easy. And breaking things is a great way to figure things out. And I broke stuff all the time when I was a kid. Some of it never got put back together. All right, well, let's just take a look at program 1. And I told you don't have to understand this code to be able to do program 1. You're given the code, you type it in, you compile it, you run it, you submit it, and you're good, right? But let's take a look at the statements that make up this program and start digging into these a little bit. This first statement says number sign include standard IO.h. Almost every time you write a C program, that's going to be the first statement. Makes you wonder why you have to put it in there at all. There's a few occasions where you don't need it, but pretty much always that's going to be the beginning. And this will confuse people a year or two after they've been doing C programming. They'll still not be sure what's going on. So I'm not going to try to get into a lot of detail about that. But basically, this thing down here where we say printf, right, this is what's called a function, okay? We're saying I want to call this function named printf, I want to pass it this thing in quotes and A and B and C. And I expect it to do something that ends up producing this line 10 plus 20 equals 30. Printf is a big function. It's got thousands of lines of code. You can download a copy of it from the web and see what it is, but it's a big program written in C, right? We did not write a description of what printf does in here, but a description of what printf does has already been written for us, and it's sitting in a file called stdio.h. And it's a file sitting in a directory called /user/include. And if I look in that directory, here's a bunch of C code. Well, this stuff in the beginning is just comments, right? And then there's these things called define and number sign if, and there's another number sign include up here, so this file is including another file. And this just goes on and on and on. And it sets up magic values for things. And there's all kinds of stuff. And we never want to like worry about this stuff, okay? But this is the kind of stuff that makes it possible to say printf. And I don't think I have p1.c here. All right, I'll just go ahead and type this in again. Alright, so there's a rough version of p1.c. And that compiles. And it executes. Okay. Suppose I don't have that include statement. I honestly don't know what it's going to do. So I get a warning message. And it's complaining about this thing called printf. So it knows printf is a built-in function. Right, it's something that we're not writing. It comes with C, but it doesn't like the fact that we're just saying printf and we haven't already told it what printf is supposed to do. That's something that's inside stdio.h. Okay, so if we look inside stdio.h, we'll see where it specifies what printf does, but it's a big, ugly set of code. So I put this back in here, and it makes the compiler happy. All right, so we're always going to say include stdio.h. Okay, this next line, we're basically defining a function. Okay, what are functions? Things like the square root function, which will let us take a number and find out its square root, or the sine function, which takes a number and tells us what the sine or the cosine or the tangent of an angle is. We can write functions, and you'll write a bunch of functions in C for different assignments. But there's always one function you have to write, and that's the function called main. Okay, so when we did this on Tuesday, I misspelled main, and it compiled, but it wouldn't make an a.out, okay, because it's looking for a main. So main is the name of the function, and we have to get into more detail than I want to explain what int and void mean. But for now, you can just imagine that you're always going to say int main parentheses void. Okay, that's the name of the function that we're writing. Okay, and then we have a curly bracket. And basically, curly brackets are used to group together sections of statements. Because I might do more than just make one function named main in here. I might make another function called my function, right? Or I might have some other include statement or something. So this curly bracket begins and ends the thing that comes right before it in the declaration of main, right? And if you don't have that curly bracket, right, all kinds of things go wrong. So we got all these errors now just because we missed one character. Okay, so again, go to the first error statement. It says it happens at line 5. Go down to line 5. So somewhere around here is the problem. Well, it's actually a little ways before here, but it'll get you close. Okay, so what does that next statement, int a, comma b, comma c, do? Those are setting up variables. Okay, it's saying a, b, and c are variables, and they're each an integer. Now you could say int a, semicolon, int b, semicolon, int c, semicolon, but you can abbreviate it by putting them all on one line after the word int, separate them with commas. All right, and then these are assigning values to a and b. So take the value 10, put that in the box called A. Take 20, put that in the box called B. And then this statement, C equals A plus B, is saying let's add A and B together, store that in the box called C. Okay, printf we're going to take apart in detail in a little bit, but for now just think of it as a way to print the values of A, B, and C. Yeah?
So it doesn't auto-format, and what is the standard 2 spaces? Is that what the end? So you do 2 spaces before.
You mean up here? So for the most part, C does not care about spaces. So I could do this, and that's a perfectly valid C program. Right? I can compile that, and I can run it, and it does exactly the same thing. Right? For the most part, white space, which are spaces, new lines, tabs, things like that, it doesn't really care about. Now it definitely cares about it, like right here. You know, if I put a bunch of spaces in here, that's going to make a difference, right? Why? Because it's sitting inside this quotation mark string, right? But over here, I can put some spaces in there, and I can come up here and I can do that. That's still going to compile and run exactly the same. So this means we don't have to worry about spacing, but it also means we can set up the spacing how we like. Okay, so how do we like our spacing? Well, indenting is nice. Okay, indenting is useful because remember I said curly brackets begin and end code. So the way I type this in, my curly brackets, my declaration of main, my include were sitting in column 1. Once I start my actual body of my program inside the curly brackets, I started indenting. Okay, I indented by 2 spaces. Most people will indent with tabs. And a tab moves you in this far. And your code would look like that. And that's fine. For me, tabs are a little too extreme. It makes it, I don't know, bothers my OCD brain. So I like 2 spaces. Some people use 4. And you can set up programs that will auto-format your code for you, okay? But I actually enjoy the process of indenting the code myself because it helps me remember where I am in my programming, right? If I'm indenting 6 spots, I know that I'm 3 levels down from the top level. That's just me. But this gets into the idea of coding style, which we'll come back to later on and talk about multiple times. But for example, if I don't say integer a, b, c, and I just say a equals 10, it's going to complain. It's saying a is undeclared. The first use of a in this function is at line 5, right here, but it doesn't know what a is. I haven't told it, right? So I could do this. I could say a is an integer, and here I could say integer b, and here I could say integer c, and that works fine. But when I'm down here in my code and I'm looking at a, b, and c, and I want to know what type of variable b is, I have to kind of hunt around in my code and figure, oh yeah, here's where I said b is an integer, right?
Why do you put the integer after the variable?
Why do you...
The integer after the variable. You know, put integer a under a equals b or a equals
Like if I did this?
Yeah.
Yeah, so that's going to say that a is undeclared. Right, so usually when it compiles the program, we can think of it as starting from the beginning and just moving through sequentially. And it won't look ahead through the whole code first and say, oh, a is an integer, and then go ahead and say, okay, a equals 10. Declarations have to come before we actually use the variables. But it's easier to read if we put all our declarations together, sort of in the very beginning. Right, so we can do this, or we could just say this, which is even easier to read. But we can't do both. Right, if we do both, it's going to complain at line 8 and say, hey, we're trying to redeclare variable a. Right, here we're saying a is an integer, but we already said that up here. So we only want to do one of those. Vertical spacing, you can do what you want with, right? Usually, vertical spacing for me is a way to sort of separate sections of my code. Well, here I'm declaring my variables a, b, and c, and there might be, 100 lines of code declaring variables. I'm going to throw a space in after that. And here I'm initializing the values of variables. I'm going to group those together, but here I'm doing something different. I'm doing a calculation. I might put some space before that statement. And then I'm going to do some outputs. I'm going to put some space before that, and then return. We'll get to that in a minute. Yeah?
So what if we declared the variables before the brackets?
That's not going to make it happy. Like that?
Yeah.
Yeah, so it's going to complain that that's not where it should be.
Okay.
Old style parameter declarations. It's thinking you're doing something totally different. So almost always, as soon as you say integer main, the next thing should be that curly bracket. And then everything else comes after that. Now, one thing we could do, but don't do this, is we could declare A, B, and C up here. Don't do that. Okay, that'll work, but that's doing something very different. That's making what we call a global variable. And that's a topic for further discussion later. But basically, when we say integer A, B, C, those integers exist between here and here. Okay, but only in this program called main, this function called main. If I have another function here, A, B, and C don't exist in that. If I move this integer statement up here, now those are global, they exist everywhere, and that's kind of a bad thing to have happen because you don't want your variables to just sort of like exist throughout your whole program. You sort of want them to exist where you need to use them and then go away. So there's this notion of programming style, and as I've mentioned on Tuesday, right, sometimes you're given a book that tells you what the programming style is that you need to follow. I don't have such a book. But I encourage students to explore and try different things and develop a style that works for them, right? And Scott may have some specifics that I'm not aware of, and if he does, obviously you have to follow those. But for example, some people will put the semicolon on the same line as the function name. Some people will put it on the next line below. All right. So C equals A plus B. This is a statement that somehow says, show me the values of A, B, and C. And we'll talk about what the percent signs mean and all that. The next statement is just saying, print out this message, right? Once we have quotation marks, it says, print out the message. That was easy, exclamation mark. This \n is a little weird. So what happens if we don't have that? If we just print out that was easy. It says 10 plus 20 equals 30. That was easy, exclamation mark. And then it prints out this N Macias at C-Tech business, right? Do you remember what I called this thing? This N Macias at C-Tech colon tilde? We can think of that as a prompt, okay? It's a thing that's saying, hey, I'm waiting for you to type something. So it's printing out my name, it's printing out the machine that I'm logged into, which is C-Tech, and it's printing out my current directory, and then a $sign. And every time that the system is waiting for us to type something, it will, almost every time, it will print out this prompt, and then it'll sit there and the cursor will blink at us. Well, our program finished, it said that was easy, and then it immediately printed out the prompt. We really wanted the prompt to be on the next line down, right? So we want to move one line down after we say that was easy. So how do we do that? Well, we could say insert, and let's put in a return. But that's not going to do what we want, because remember, it doesn't really care. Actually, I don't know what it'll do. I don't think this will do what we want. Right, so it's unhappy because it's inside a quoted string, and there's this carriage return in there. So there's a trick we use when we want to actually print a new line. We say \n. And \n is just a way that we specify go down to a new line. So if I do the following, if I say that \n was \n easy, what do you think it's going to do? Yeah, it's going to put a new line between each word. Right, say that was easy. And there's a few different \/ characters. You'll see \t means print out a tab. So move over to the next tab position, which is usually multiples of 8. So that's one way to help line things up. But generally you'll see this \n at the end of print statements. Same thing up here, where it printed out the values of A, B, and C. We wanted to go down to a new line and then print out our message saying that was easy. All right, and then return 0 is another one of these things that for now we're just going to say we always have to put this at the end of our program. What it's actually doing is when we say a.out, the operating system, big C program, right, that's already running, is jumping down and saying, let's execute the function main. Let's run the code that's inside here. And it's going to keep doing that until it gets to something that says return. And when it gets to the thing that says return, it's going to go back to the operating system. In this case, it's just going to print out the prompt again. So /a.out, it started running our program, printed out 10 plus 20, printed out that was easy. The return said, okay, go back to the operating system, and it printed out a prompt. And it turns out if you don't put that return statement in, it gets added for you. Right? But it's good practice to put it in.
Why 0?
there's kind of an unwritten convention that 0 means everything is good, and non-zero means something went wrong. And when we return 0, actually the operating system can look and see what that value was that was returned. So what's your favorite small number?
8.
8. Okay, let's return 8. All right, so we run that 10 plus 20 equals 30. That was easy. If I say echo $? I get an 8. Okay, and whatever value you return from main, you can get to that by saying echo $? Only works once, because if I do that again, the echo program returned a 0. Right? Every function that you run returns a 0. So if I say GCC P1.C and I look at $? Nothing went wrong. Okay? If I say GCC ha.c, no such file or directory, look at $? It's equal to 4. It means something went wrong. CSE 224, we use that a lot. We start digging into those kinds of behaviors.
What's that course?
CSE 224 is programming tools and something else. It's the fall course in the 200 level CS sequence. So it's shell programming, it's debugging, it's scripting, it's more C programming. It's a fun course. All right, so we're going to return 0. So here's a question.
So it doesn't matter if it's in parentheses or not, right?
Actually, return is a funny instruction. You can just say return 0 and that'll work fine. Right, and some people get upset that it's put in parentheses. You can actually find like long discussions online with people yelling at each other about why you should or should not put it in parentheses. I always put it in parentheses. Actually, Scott did not, so maybe you shouldn't put it in parentheses. But I always do, and even if I try not to, it'll end up happening. All right, so here's a question. What if I don't initialize A and B? What if I don't say A equals 10, B equals 20? I just say C equals A plus B and print out A, B, and C.
Well, the specify the percent I would think would look for an integer, so I don't know.
So it's going to look for an integer, and we are saying A is an integer, but we're not giving it a value. So what would you think or hope or theorize the value of A might be if we don't give it a value?
Just A.
But it's got to be an integer, though.
Oh.
Right?
0.
0 is a reasonable default, right? And in fact, on some systems, it will initialize to a 0 automatically. But that's not guaranteed. And I don't know what CTEC will do, but my favorite statement, let's find out. Well, it definitely didn't initialize to 0. And if we run this again, got different values. So A, B are initially basically random.
It should be negative value.
Yeah, they seem to be negatives.
But it's
And they seem to be pretty close in value each time we do this.
the output. Why is the output positive?
Yeah, that's negative plus negative.
It should be a negative.
And the output is positive.
Did you just break math?
Yeah, we broke math. So we're about to launch into looking at data types. And what we're seeing here is what's called an overflow. Numbers can only be so big on a computer, okay, in C at least. And they go roughly between plus and minus 2 billion. And this is negative 1.2 billion plus negative 1 billion, that's negative 2.2 billion. That's too small a number to represent. It ends up overflowing and it becomes a positive number. And let me make it a little more. see if I can count. So I think that's 1.2 billion and 1.2 billion. Let's just add those together. And we get a negative number. Right? We should get 2.4 billion, but 2.4 billion is too big. And the way numbers work on computers, and this is what we're going to talk about next, if we keep increasing numbers, once we get up to this roughly 2.2 billion, which is the largest number, if we add one more, we get negative 2 point something billion. And then we start increasing our way back to 0, and when we overflow again, we come back down. Same thing when you're decreasing. If you decrease down to negative 2.2 and you take one more away, you suddenly wrap back around to positive.
So this has nothing to do with being int versus long?
Yes, it has a lot to do with that, actually. So if, and well, yeah, but I'm not going to do that yet. But if we made these long, it would be a larger range before it overflows.
Okay, so, okay.
Yeah.
The answer will be okay for this one possible.
All right, so two things we've seen here. One, we have to initialize our variables. Okay, really, really important. And it's difficult to remember that because, again, on some systems, things are initialized to 0 automatically. But that's not part of the C standard. And if you work on a system that initializes things to 0 and you forget to initialize them yourselves, you get your code all written, you put it on the CTEX server and try it out, and it blows up. Right? And you got to figure out why that's happening, and it's because possibly these initializations weren't done. And two, there's a limit to how big our numbers can be. All right, so that's a really good segue into this business of data types. All right, so we make something an integer, we can give values to it. So declaration statements and assignment statements. And we can actually do an assignment when we declare our variables. For example, we can say integer total equals 3. That's the same thing as saying integer total semicolon total equals 3 semicolon. Well, the other thing that I didn't make explicitly clear in here is that most of our statements end with semicolons, right? That's how the compiler breaks up our code into statements because, again, you could put everything on one line. Right, so the semicolons say, here's the end of this statement. But, you know, integer main void does not have a semicolon at the end. Number sign include does not have a semicolon at the end. There's exceptions. And you just kind of learn those. But most statements end with a semicolon. Right, so I could do this, and this would work exactly the same as our original program. Here I'm declaring A to be an integer, but I'm giving it a value of 10. I'm declaring B to be an integer, but not giving it a value. But then in the next statement, I say B equals 20. Right, so different styles, different reasons why you might do one versus the other, but equivalent behavior. This is something else to keep in mind. For any given programming assignment, there are probably, it's not limitless, but there's a huge number of different ways to write C code that'll do the same thing. Okay, and in general, a lot of these are neither better nor worse than any other. It's just different ways to do things. Some of them might be a little more efficient, some of them might be a little less efficient or take more memory, but I think it's useful to sort of think about different ways to do things. And if you see a set of code that does something and you think from what you understand of C there should be a different way to write that also works, give it a try. Right? And if you really think it should work and it doesn't, ask about it. Right? This is a really good way to learn the details of the language is explore it on your own. Right? Do something that should make sense, and if it doesn't work, then try to figure out why. All right, so what types of variables can we have? So original Kernighan and Ritchie see integers, which is what we've been working with. Longs, which are a bigger version of integers. Okay? Shorts, which are a shorter version of integers. Unsigned, which is a version of an integer that can only be positive or 0. Normally integers can be plus or minus. But sometimes we want integers that are not negative, and we can make them unsigned. Characters, which hold a single letter or digit or symbol, a number sign, an exclamation mark, the digit 3, the letter X, just a single character. Floats, which are real numbers, and doubles, which are also real numbers, but can be larger and are more precise than floats. And then there's signed numbers, which we can make explicit. There's void, which is not really a data type at all, and Boolean, complex, imaginary, we're not going to worry about those. Mostly integer, character, and double is what you'll use in most of your code. Integer, character, double. Okay, integer for whole numbers, double for real numbers, and character for single symbols. All right, so signed versus unsigned. This gets a little confusing sometimes. It comes up a lot in computer science courses. It'll come up some in Engineering 270, the microprocessor course. But it will make sense perhaps over time. But basically, signed numbers can be positive, negative, or 0. Unsigned can be positive or 0, but not negative. And we can have signed or unsigned characters, which is kind of weird. Character is supposed to hold the letter Q, right? The digit 7. But remember, everything in the computer is basically a number, right? It's mostly just a bunch of integers, or maybe a real number. Short int uses fewer bits, so it has a smaller range. A long int uses more bits. A long int uses even more bits. But let's play with something. I'll go ahead and put void in there. Don't worry about what most of this means. Most of it's just we'll talk about for statements later, but my goal is to basically 100 times I want to do the following. I want to print out the value of A, and then I want to multiply A by 2. Okay, I'm just going to do that 100 times. This is CTEC. Okay, so I ran this program. I printed out 1, 2, 4, 8, 16, 32. It's doubling our variable A each time until it gets up to about 1 billion. And then when I double that, it jumps to negative 2 billion. And then when I double that, I get 0. Right? And this is the fact that an int can only go up to about 2 billion. Right? And when I tried to double 1 billion, it was actually too big. It rolled over, it overflowed and became negative. When I tried to double that, it basically just said, I give up. And it just said 0. if I say short integer a, and I run that, it goes 1, 2, 4, 8, 16, 32, got up to 16,384, doubled that, should have gotten 32768. Instead it went negative,
Why?
and then it gave up after that.
Why does it go to negative?
It goes to negative because it does. Well, we may see why when we start looking at the actual way these integers are represented. But the fact that I said this was a short int, it can't be as big, right? It gets up to about 16,000, then it overflows. Now if I say this is a long int, it overflows at the same place as a plain int. If I say this is a long int, and this may not work, but that's for different reasons. All right, so I don't want to go there. Failed demonstration. It's actually doing the multiplication, but my print statement is assuming I'm printing an int. So I can change that and make it print longer. But a short definitely cuts down the range of it. Long int technically can be a lot bigger than an int. So we can specify different types of ints.
So then how do we make something unsigned?
You can make it unsigned by saying unsigned.
Oh, just type that.
Yeah.
'Cause
In
that
fact,
would be
let's.
4 billion, right?
Yeah, but there's a problem here. So let's make this an unsigned short. So it got up to 16,000, and then it did get up to positive 32,000, right? When we did this before, it went from 16,000 to negative something, and then it went to 0. Here it actually doubled this, and it got the correct value. And then when it tried to double that, it went back to 0. So unsigned gives you a longer range on the positive side, but it doesn't give you any negative values. And let me just push my luck here. No, I'm not going to push my luck because it won't work. Okay. So two kinds of integers, signed and unsigned. Mostly we're going to deal with signed. Right? We're just going to say int, and that's going to mean it's signed. And usually a plain int, plus or minus 2 billion, that's a good enough range for most of what we'll do. Occasionally you need longer, and so you say long. There's really no reason to say short int. But when memory was precious, when you had, 1,000 bytes of memory on your system, if you only needed a short int, you would say short int. And you'd save the memory for other stuff. 16 billion bytes on your CPU's memory. Don't worry about shorts. All right, so remember, byte is the fundamental smallest piece of storage, right? And a byte is composed of 8 bits. A bit is a single 1 or 0, binary digit. So we can ask, how many bytes are we using for these different types of variables? So an int I've suggested is 4 bytes. Well, if a byte is 8 bits, how many bits do we have with 4 bytes? 8 times 4, 32 bits. So 1 byte equals 8 bits. 4 bytes equals 32 bits. And it turns out on this system an integer is 4 bytes. That's not inherent in C. That depends on the system you're running on. On another system, an integer might only be 2 bytes, which would be 16 bits. But on our system, an integer is 4 bytes, 32 bits. So if we were to write out those 32 bits side by side, Right, that might be what an integer looks like. It's just 32 ones and zeros. All right, well there's a command in C called size of, a keyword called size of. And size of, you can give it the type of a variable. Don't give it a variable itself, but give it a type of variable, int, char, float, double, right? And it will tell you how many bytes that type of variable takes. And so here's a program we can run that will basically tell us how many bytes we're using for each of these different types of storage. So size of bool equals, and it'll print out the value of this thing over here, size of bool, which should tell us how many bytes are being used for a Boolean. And down here it'll say size of double equals, and it'll tell us the result of this size of double statement. So I think I have the code for this. But let me see. I do. All right, so really fast typing there. So here's a program called size.c. And if we compile this and run it, it should tell us the size of these things, except, yeah. So I'm doing something here that I don't know if Scott tells you to do later on or not, but if I just say gcc size.c, then I get an a dot out, right? And my a dot out from pa1.c has been overwritten, right? So I'm doing something here. I'm using a switch, right? I'm saying -o size.c. This is saying compile size.c, but put the output in this thing called size. So when I say that, now I have a program called size that I can actually run. So I can say /size and it'll execute it. If that doesn't make sense, just do gcc and do a dot out. Okay, so here's what size tells us. So a character takes 1 byte, a Boolean takes 1 byte, short int takes 2, int takes 4, long int takes 4. Long int actually takes 8 bytes, so 64 bits. Float is 4, double is 8, long double is 12. All right, well, what does this mean? If we have an integer that only has 1 byte, 8 bits, how big a number can we store in that? We saw if we only have 4 bytes, we can go up to about 2 billion, right? If we had 2 bytes, a short int, we could go up to about 16,000. So where do those numbers come from? So let's think about just a single byte. 8 bits. So what are some possible 8-bit numbers? Yeah, so here's an 8-bit number. Here's another 8-bit number. Here's another 8-bit number. So how many different 8-bit numbers are there? How many ways can we write down 8 ones and zeros? Yeah, so why is that, you know? Yeah, so if there's 8 bits, it turns out there's 2 to the 8th possible ways that we can write this down. Now if you don't know that, here's a different way to think about it. Suppose we have a 1-bit number. Okay, somebody give me an example of a 1-bit number. 1. Are there any other 1-bit numbers? 0. Any others? That's it. Those are your only 1-bit numbers. Okay, suppose we want a 2-bit number. Well, we can think of it as some bit over here followed by some bit over there. This bit has got to be either a 1 or a 0. The bit before it has got to be either a 1 or a 0. So it could be that I have, zeros in that first position, or it could be that I have 1 in that first position. So I had 1, 2 1-bit numbers. I've doubled the amount by adding another bit. If I want to add a third bit, my 3-bit number could be these 2 bits with a 0 in the front, or it could be these bits with a 1 in the front. So I've doubled the number of possibilities again. So each time you add another bit, you double the number of things that you can represent. So this is why when you have 8 bits, you have 2 to the 8th possible numbers. If you have 16 bits, you have 2 to the 16th possible. 32 bits, 2 to the 32 possible. So 2 to the 32 is 4.29 billion. 2 to the 16 is 65,536. 2 to the 8 is 256. So yeah, 8 bits, 256 possibilities. But that doesn't really tell us how big of an integer we can hold, because it really depends. Now, if this is an unsigned integer, we'd like it to be positive or 0. So we could start from 0, 1, 2, 3. If we've got 256 possibilities, we can go from 0 all the way up to 255. But if we want it to be signed, we're going to take roughly half of those combinations and say these are negative numbers, and half of them will be positive or 0. And so even though there's 256 combinations, we're going to spread them out to go basically from like negative 128 to positive about 128. It's actually 127. Or maybe we only care about even integers. And if we want even unsigned integers, we could say we're going to have our integers represent the values 0, 2, 4, 6, 8, all the way up to 510 or 512. So translating a pattern of 1s and 0s to a number, there's standard ways that we've agreed upon to do that. Okay, but there's nothing sort of inherently natural about that. It's really convention. So let's talk about number systems. So the average person has slightly under 10 fingers, but the majority of people have 10 fingers. So we usually work in base 10, because when people started doing arithmetic, they used their fingers. And so they came up with symbols for how many fingers you have, and we have 10 fingers, 10 possible symbols, 0, 1, 2, 3, up through 9, right? And then if we want to represent the number 10, we don't have a new symbol for a 10. We do something very clever. We write this. Well, this is a symbol for 0, this is a symbol for 1. How do we get the value 10 out of a 0 and a 1? Well, we have a convention. And the convention is we have the 1's place, we have the 10's place, we have the 100's place, and so on. And when we list a series of digits side by side, we understand the rightmost digit is the number of 1's, the next digit is the number of 10's, the next digit is the 100's, and so on. Anybody ever seen that number before? Probably not. Is there anybody who does not know what that number is, though? We all know what that is. If we wanted to add 1 to it, we could do that. If we wanted to multiply by 2, we could do that, even though we've never seen that number before. I've never seen that number before, right? But we can still use that number. We know what it means. Why? Because it's not just a random set of digits, right? This is 7 times 1 plus 1 times 10 plus 9 times 100 plus 2 times 1,000 and so on. Okay, so the terminology is weighted positional notation. Each position has a power of 10 corresponding to it, and this number is the sum of each digit multiplied by the corresponding power of 10. So we learned this in grade school, right? And it works really well. It lets us do pencil and paper addition and subtraction and multiplication and division, and lets us compare things. And we can take this number and we can take those two numbers, and we can immediately say, oh yeah, this number's bigger, right? And we know that because the first digit was bigger. So all these things work really well. Well, computers don't have 10 fingers, right? If they had fingers, they would probably have 2 fingers. So, so we just work in a base 2 system. But we do exactly the same thing that humans do in base 10. We use weighted positional notation to represent larger values out of these small values. So here's an 8-bit number written in binary. This little 2 over here on the right is saying that this is a binary number. Because it could be 1,100,101 if it was decimal. And so each digit corresponds to a power of 2 instead of a power of 10. So this is the 2 to the 0s, this is the 2 to the 1s, the 2 to the 2s, and so on. So this is actually, this digit gets multiplied by 1, this gets multiplied by 2, 4, 8, 16, 32, and so on. And then we take the value that we get by multiplying the digit by the power of 2, and we just add those together. And the result is the value of that binary number, which turns out to be 101, which if we didn't know what this was, might be a binary number, right? But we put a little 10 here to say that's base 10. So we've seen this in 120, right? But it takes on new significance in the realm of a programming course, perhaps. So this is an unsigned integer. Okay, just straight weighted positional notation. And so what's the largest unsigned integer we can have? Well, make all your digits 1. Okay, if you have 5 decimal digits, what's the largest value? 99999. Make each of your digits as big as possible. 8 binary digits, make each digit 1. And this is equal to just 1 multiplied by each of those powers of 2. So it's 2 to the 0 plus 2 to the 1 all the way up to 2 to the 7, which turns out to be 255, which for various reasons turns out to be 2 to the 8th minus 1. And so that's a formula you can always remember. For an unsigned integer of n bits, the largest value is 2 to the n minus 1. So 8 bits, 255, 16 bits, 65, 535, 32 bits, 2.2 billion roughly. Okay, unsigned character is 1 byte. We can use this to hold numbers from 0 to 255. Characters are usually used to hold characters, but we could use it like a really, really small integer. Alright, so just plain unsigned int is 4 bytes. We saw that with the size program. Largest value is 2 to the 32 minus 1, sorry, 4.2 billion. Smallest value, make all your bits 0. And 0 times 1 plus 0 times 2 plus 0 times 4, that's just 0. Alright, 64 bits, we can go up to 18, whatever that number is. 2 to the 64th minus 1. 18 skrillion, let's call it that. Okay, got the basic idea? Alright, let's take a 5-minute break. Let's talk about negatives when we come back.